Before that time.
The physics behind, for example,
another question
the actual change in mass.
under the ultimate question about
During
the
the course of 7 years, the book was put together.
It was astrophysicist Neil deGrasse Tyson who said, "Math is the language of the universe. So the more equations you know, the more you can converse with the cosmos." Here in the Scholars Chair is Dr. Katie Gurski from the Department of Mathematics at Howard University. Tonight, a conversation about math as the language of the universe.
Let the conditions of inequality that we suffered under, when we are the oppressor, the dominant class, let's not impose that injustice on the others.
Anybody think that you could have a just system without giving women their rights?
Everyone has an opinion, and we sit around the marketplace and talk about opinion, but what is truth?
With the shareholder, their goal is similar to the business, to maximize profit.
That belief becomes a context for a development of knowledge.
Say physics is the DNA of technology because the rules for how you build new technology starts in physics.
Because Quran challenges the people. It's not only the people of the book, it challenges Muslims.
We say secular, they hear godless.
Right.
What was intended?
Watch the Scholars Chair every Monday night. And here is your host.
Welcome to the Scholars Chair, Dr. Gurski. It's good to see you in the studio.
Thank you for having me.
I want to ask you the question that we started with at the top. Dr. Tyson said that math is the language of the universe. So he said the more equations you know, the more conversation you can have with the cosmos. Do you agree with this assertion? Or
I'd say it's true as far as we know right now, that certainly the way we try to describe our world is in mathematics. And if it's not mathematics, that'll be kind of fun to find out later on, too. But right now, yes, the way we understand how we make predictions, everything is mathematics.
That was the method used by Einstein, wasn't it, for his theory of relativity? Wasn't it a mathematical expression?
Yes, it was.
Yeah.
Yes.
So when I saw that on a piece of paper, I said, "This is crazy." It's better when you heard the words to it. Tell me, what is math to you, and how do you teach your students about what is math?
Math, as I say, it's a lot more than what you think. I mean, a lot of people think of math as just adding numbers. But it's a lot more than that. It's about patterns, recognizing what's there, what should be there, that's not there. And a lot of it is just trying to put together a logical order. See that, as I said, you could make predictions, you know. And as we found out just this year, Einstein's predictions, some of them were right.
Some of them were right.
Well, there's still, things to be verified, but I mean, some he was able to show right away, but
it's not a perfect theory.
I don't know if there is a perfect theory out there.
That's exactly right. Tell me, what excites you about math as a teacher? And
I have a lot of fun with it, both in teaching and in doing research. And teaching is trying to explain to the students something and seeing that little light bulb go off in their heads that when they finally get it, understand it. And a lot, since I teach college mathematics, is to show them that these little tiny mistakes, that if they can catch them, they can see the whole picture still, that they can be good at math. And then in the research, it's fun because you're working on something, trying to explain some problem, trying to solve something, and it may be take a lot of work, but at some point that little light bulb goes off in your head too, and you're able to do it.
So the discovery of the process. Tell me about the objective. What is the objective of math?
As I said, it's to describe what's going on in the world, to recognize your patterns.
Would it be to bring harmony and order to it, or would it be to show unity in it, or
Well, until you get to chaos, and the chaos theory, and there's a lot of mathematics that describe what's going on there, and that's bringing disorder. But I think it's more how we are trying to understand the world, whether or not it's bringing harmony.
So it is symbols actually that describes what we're observing, or minimally.
Right. I mean, and that's into just like your numbers. Your 1, 2, 3, 4, 5. I'm counting. 5 blocks. I'm counting. 5 wildebeest. I'm counting. Whatever I happen to be counting, and to all the way to, I need to make this prediction of, what's going to happen when I throw this rock off the cliff, or what's going to happen in the stock market later on, or anything.
Katie, what I was hoping for, what I'm hoping to solve in my own neighborhood is that I have this camera that's located, a traffic camera that's located on the corner where I live, one of the corners I have to turn. And I want to know, what is the probability of that camera catching me, making the wrong right turn, 7 days out of a week?
It's far too high. The camera seems always to be working whenever I do something wrong. So.
I think that's right. Yeah. Tell me about the skills of a mathematician. What are the opportunities available for a skilled mathematician?
Oh, everything. I mean, it depends, what exactly it is, depends on, what level of math you've learned. You come out of high school and you know your math well, you can go do anything. In college, you're prepared. If you have a solid high school math, you go through in college and say you're a math major, or learn enough math to go off into, it helps you do all the sciences. If you go off and get a math major, people are like, oh, what do you do? What do English majors do? Well, math majors after college get hired to do things other than math, and people want them because they've been trained to think in this very logical pattern and to problem solve. And then you can go on and work more with science, and go on and you have to go all the way to get your PhD really to do math research in this country. But you can do anything.
What are we studying in math research these days?
Everything. I'm studying problems to do with modeling astrophysical flows on a sphere, doing some problems with that, and I'm doing some problems with describing why there's racial disparity in which women get HIV, and working on trying to make predictions for when you should give intermittent preventative treatment for malaria. I mean, you can do it everywhere, everything.
Yes, I think that was an interesting idea. I never thought that you could manage diseases by using mathematics.
And it's a great way, because there's a lot of things that it would be inhumane not to treat people, right? But you can test your theory of not treating people in math and not hurt them.
Yes.
There's a lot of things where it's just like the idea in sciences. You need to do non-destructive testing. Say, like you want to show, unfortunately, whether your nuclear bomb is working or not.
Yes.
You do not want to explode that.
You don't want to blow up anybody.
You do not want to do that, but you want to do a simulation of it, now understand it, and that's all mathematics to do that simulation. And it builds into all the other fields too, to make that simulation happen.
So engineering, computer science,
absolutely.
all these fields that
not just that. I mean, all the way to movies. All these great Disney movies and all these other ones with the computer animation, that's mathematics.
Yes.
And if you ever look at them, you'll see as the years go on, the water flow looks better, things like that, because they're adding more math into it, and they're hiring more mathematicians in. Yeah, but it's very hard problem to describe water flow mathematically, but which is why it's not quite right yet. And but everything. I mean, predicting your weather. But as I said, the movies motivate the kids.
That's
I think.
exactly right. And someone also said music was also a part.
Oh, absolutely, yeah.
Actually kind of give a, it has a pattern that mathematics can be described in. Tell me about how math sharpens your analytical skills. Give me an example of that.
Well, I mean, if you're going to, say you're going to break a code, okay, you need to figure out what the pattern is, right? And you need to be able to figure out what's most likely to be repeated, what's not most likely to be repeated. You know, you have your statistics and you know how likely something is an E, if it's you know you're doing letters and all. That's a lot of it. And there's also the training of looking at a problem and saying, this is how I phrase a problem so I can test it. So I can verify whether the problem is being set up correctly. I mean, that's a big part, right? Before you go spend $1 billion on some study,
Trying to solve the
$1 million or however many money, you know, to see whether or not this drug is helping the community, or you need to know, well, how many people and what kind of people to test it on, what kind of variables are important. You know, how many people of, you know, how many kids of 5 to 6, you know, I need to include in that study. That's all math.
How interesting. You have to, there's a lot more stuff I'd like to get into more details on. That's fascinating. Tell me about math as a system used to better solve problems. Tell me, you know, I know you've given many examples, but tell me something that is close to you and or you see a colleague working on that can that people here in our audience can understand.
Well, as I said, the examples I give I'm doing with the disease modeling and all. But I mean, you can even talk about the one if anybody remembers the game Tetris. I'm gonna, you know, packing. What's your most efficient ways to pack things? You know, the sphere packing problem is a big problem. Another math problem that you don't think about is, you know, how can you hear the shape of a drum is is a math problem, right? So, yeah, given this, and a lot of things, you know, given some signal, can you figure out where it's coming from? Can you figure out all sorts of missing information from that piece? So
how is it that you think that we're having so much challenge in predicting our elected officials? Is this because we're really poor at math? Is that what's happening?
No, it's because there's a lot of data that they didn't include. It's the same thing with the weather, right? When you're predicting the weather, you know, they've got all these different measurements systems everywhere, on the top of the ocean, on the bottom, under the ocean, up in the sky, everything. And there's a lot of noise with the with each of the data sets that they capture, and they're trying to say, well, how much noise do you filter out? What is just, you know, this satellite's not doing well, or, you know, this buoy is sending out erroneous information. How do you weight that? And you see with these different models, they weight the different ways, and you say, oh, DC's going to get hit by snow, and then actually we get hit by a lot of rain because they ignored buoy number 97. That's what happened with the election. We ignored one group of people out there until much too late. So
I see.
Yeah, but I mean, they try to capture it in doing the polls, but you know, a lot of people don't want to be polled.
So you can get the equation wrong, or so to speak.
Right. If you don't, even if you have the equation right, if you don't have the data to put into it, you're going to get the wrong answer.
Describe to me a discipline that relies on qualitative and statistical reasoning. I know that you've been talking a little bit about it as we go along here.
Sure. As I said, I have a lot of good friends who do statistics. Some work with like the National Cancer Institute, helping design clinical studies, helping verify the data, helping verify the studies. But you also see it, you use it like when you're doing signals. Your TV signal, right? A lot of what we send in a TV signal doesn't really need to be captured pixel by pixel. How do you compress it? That's a math problem. Statistically, you know, probability-wise, if I ignore this piece, how likely is it to be a problem? So, everywhere.
It's everywhere. You know, you use mathematics in almost every discipline that there is. I mean, even in medicine, I would surmise. What do you think is you know, one of the challenges I had when I was taking math is I had this very tall math teacher that would come into the classroom and greet us, good evening students, and that was the last time we saw the person's face. The rest of the time we were looking at his head, and he started from one side of the blackboard, and it wasn't a blackboard, it was one of these white magical boards. And he started from one side of it, and he started with the equation. He ended up in the middle of the room, and then he went on to the other side of the room, and he just continued this process through the whole class period. And then he turns to us at the end and said, "You got it?" No, we didn't get it, and it was really interesting. He was assuming a lot on us. He was saying that. And in fact, when we would ask him, you know, where did you get this number? He said, well, you should have just understood that, you know, this happened and that happened, and I got this number. You should know that. I found that very interesting that he eventually had to teach us, right? Tell me, what is it that teachers can do that best educate students in a classroom situation?
I don't think that's the right way to go. I mean, you learn eventually, the farther you get at math, you get so that just, you know, having a fire hose worth of information is what you need, and that's the way to get it. But that's not the way to teach math at an earlier stage. You need to show them some examples. You need to explain why they care about this problem, where they're going to use this particular piece of mathematics that you're doing, and you need to make them practice it right away. And then somehow motivate those students to go home and work on it and work on it and work on it and work on it, because that's all it is.
Yes.
It's like, you know, if you're going to become a super basketball player, you have to dribble and practice your dribbling until you can dribble the ball without looking, so you can run up the court and make that slam dunk.
The fundamentals are so basic.
You have to, and every day you have to go out and practice. And that's the thing that you know, they're like, oh, well, I'm not any good. I'm like, well, you're not any good because you haven't spent the hours practicing, right?
Practice.
Right, and you get rusty. Just like I can't go out and well, I've never been able to slam dunk a ball, but you know, I can't necessarily make a layup unless I have been practicing, right? So, and that's the way the math is that if you aren't using it, it gets rusty, and it's harder to go about it. But that's the big thing, is the motivation, I think, in telling the students where you're going to see it, why they should care, why they should practice,
I should have
and
had
make
you,
them
Katie.
do it.
I should have had you as my instructor. You know, one of the things I found interesting that I was looking at a class example in a classroom setting. Somebody was teaching me about compound interest rates, and I said, I will never use this again in life. So let me go pass the test and off to the next thing. But what it turned out is that I was able to purchase some property. And the bank was doing a very interesting things with interest rates. It was like a 5 or 6 day spread where the interest rate was actually increasing. You know, it's like the first, you had that particular interest rate. If you paid on the second, you had that particular interest rate. The third was the other. And we thought that we would just be fine just paying it within, you know, 5 days, you know. But it was amazing, the difference between the first and the fifth. And it took a spreadsheet to actually figure out that the interest rate, by the time if we paid it on the fifth, our mortgage would be way beyond what we thought it was going to be, you know. So it was one of those things that a little bit of patience an examination about what is going on out there. And I understand that we are living in a time where people are using extraordinary interest-bearing financing to just capture people's property. Do you understand that in terms of relationship to understanding mathematics?
Oh, absolutely.
Yeah.
I mean, I just taught, this compound interest to my students.
Oh, good.
And I use it as an opportunity to explain why they should pay their credit cards off every month, right?
Right.
How that interest compounds in that purchase that they made, that they could be, rather than buying that pizza, they're paying for 20 pizzas if they don't pay it all off all at once.
Yes.
But and to understand, as you said, you go into a bank and you need to understand whether or not the deal they're giving you is any good, right? And it's difficult if you can't follow that. And just like, if you go some places, they'll tell you the sale and it's 90% off today. Well, but really it's 90% off this, and it's 90, and it actually isn't. You're paying really 70% of the original cost, but the way that they've staggered it, you don't know it's not a good deal unless you do the math.
Absolutely, and they just assume that you know math.
No, they assume you don't know math.
That's right.
That's what they're assuming. Yeah.
Katie, I think you're right. So tell me about the different levels of math, because we have people who think they have math once they have communication skilled mathematics.
Well, it's very. I mean, it's a continuous spectrum here. That's a nice math term, is continuity here. Sure. But you start, with your concrete ideas where you can count things, and then, they move up and they learn that there's more numbers between 0 and 1 than you thought, and you learn about fractions and decimals, and then you learn there's an infinite number of things in between there. And you move along, it starts getting more abstract. And that's where people start faltering if they don't know the concrete stuff. Because by the time you get to college, it becomes more abstract. I try to make it less abstract by showing them where the applications are going to be used, and I do that in the graduate classes I teach too. But some of them I don't know the applications for where it is, because people haven't invented them yet either for some of them. That's part of the math is, you develop the math and then you figure out what it applies to later.
Yes, you're using it, but you now have to categorize it. Yeah.
Right. But I mean, what people think of as math is very different. I mean, what I do have a lot of derivatives, a lot of integrals, a lot of big systems and calculations. And what my office mate does, he draws these pictures on the board and has all these simple numbers, and it looks nothing like the mathematics that I do. But it's a very powerful mathematics as well. So it's just, it's hard to describe what level, because it's such a broad spectrum, because it's everywhere.
It's everywhere. The levels in the way I was thinking about it is, high school, algebra, calculus.
So algebra is your first step to abstract thought.
Okay.
And that's what you're doing with a spreadsheet, is you're doing algebra with your spreadsheet. Right. You've got, take whatever's in this spot and multiply it by what's in this spot, what's in this spot. Those are your variables that you're doing. It's just not written down as an equation. It's written in spreadsheet.
Yes.
But just everywhere you would use a spreadsheet to calculate the cost, say your
mortgage rate in 10 years.
Not just your mortgage rate in 10 years. Say I'm running a business and I need to give a quote for how much it would cost to do this job, right? And you go to your spreadsheet and you figure it out. That's algebra. You're doing algebra to figure out what it should cost. But that's the first thing, is where you've got this unknown and you're trying to solve for it. What's the price I should charge to make a profit, because I want to make a profit, right? What's that price I should charge? And that's the first step, and recognizing that all those rules you learned before still apply. And that's where the students get lost too, is because they don't understand, oh, there's all these awful rules that you have to learn, that, you know, you can group the numbers this way and it's the same way if you multiply them and then add them, or multiply them and add them, and, you know, all these different things. Where is it, why is it important? Well, it's going to be important later when you start abstracting things and you don't always have the numbers and can't do all the intermediate steps. So
Wow.
The algebra is just building, adding one little layer on top of all the other math that you've learned.
Interesting. I never thought about it that way, but certainly to solve for the variable is what it's all about.
Right.
Solve for the unknown, as some have said.
And when you go on, you know, to calculus, what is calculus about? It's talking about how things change, right? You've got your variable. Well, how is that variable changing? And that's what calculus is all about.
Interesting. So tell me about the many uses of these functions. I wanted to maybe talk about what is algorithm and what is that function.
So an algorithm is, it's basically a story. It's saying, and it's, well, it's more than just a story. It's saying these are your instructions. Okay, I want to go from point A to point B. Google Maps is going to tell me to turn right, left, right, left, right, left. Well, that's what my algorithm is going to do. It's going to say, you start with whatever number you start with, and then you do these certain things to get to the end product. And the beautiful thing about an algorithm is then you can give it to a computer who doesn't mind doing it over and over and over and over again.
to predict an outcome or
right.
to solve for an outcome.
And because there's the way that our world is now, we need to do these computations a tremendous amount of times to be able to make our predictions.
Wow, I tell you, this is the reason why we need you to come on this Scholars Chair more often, because we have to have someone that can explain this stuff to us. Tell me about geometry. What is that?
So geometry, I just became acquainted with it again after all these years because my son's learning it, and it's really just a logic, a step of, this is what these are the little pieces that you have, and I want to get here. How can you put them together? So, but you're doing it with words, okay? I've got this triangle. Can I prove that these two angles are the same measure? You know, and you've got all this different structure, and I know these different pieces. Well, how can I put them together with these different rules, these different definitions that say that those things are okay? Okay, and that's what I'm talking about, writing a problem so you can test it, right? It's your, and that's the whole idea of having a hypothesis, right? You know, is a hypothesis is just a theory you can test, and that's the whole idea. Is I have this idea, I think these two things are the same. How do I show it's true, or how do I show it's not true, which is equally important.
Yes, to make sure that it's correct. Exponents, what is that?
So I think the better way to describe exponents is, like say you're looking at bacteria, how they grow, right? If you're trying to describe how they grow exponentially. You need a function that says like they double, and that's what exponents do. The base part is just saying how they change by this quantity.
So,
2 or e or whatever, right? Right, and the exponent is the part that's the varying. So that's the part that's increasing. The base is the part that's staying the same. So saying whether, you know, a rabbit has 1 baby rabbit, or 2 baby rabbits, or 3 baby rabbits, but then, you know, as you go along in the generations, that's the exponent part.
Wonderful.
So it's describing a lot of natural things. You can also go the other way, not just, you know, your increase, describing like radioactivity, how your radioactivity, how it decays. As we discover, you know, with like this hazardous waste, it's hazardous basically forever, because the way it decays is exponentially.
You have educated us. Thank you so much, Dr. Gurski. Tonight we've been talking about math, the language of the universe, with Dr. Katie Gurski from the Howard University. And you can see more on Scholars Chair online at our blog at read1communications.com. I am Khalil Shadid. Good night.
Amazing.